What we work on is simulating quantum dynamics in the condensed phase. So an example of that would be, for example, simulating quantum effects on the motion of hydrogen atoms in liquid water. What I love about it is it's very new, because this area of theory, you couldn't actually do it at all until very recently. It's a very strange world if you look at this quantum motion in say, a liquid, because it's partly classical and partly quantum. And to better describe this, we and other groups have had to import basically new physics in, based on something called path integral theory. And using this, we're able to simulate all kinds of things that previously people couldn't simulate. So it's sort of a really new frontier that we're working in. Yeah, the main contribution it's making at the moment is allowing people to simulate things that previously they thought they couldn't simulate. So for example, there's a group in UCL that was able to simulate diffusion of water on a metal surface using this technique that we developed. They're able to find all these tunneling effects, for example, using this path integral technique. There's another group, for example, in Yale that's looking at nonlinear spectroscopy, again using this technique. So that's the main thing, I think, main effect that we're having. We're coming up with new simulation methods, also concepts that you need to sort of base the framework of the simulation on. And these have been taken up by the research groups. All of this work basically comes out of this new kind of theoretical framework, which we call Matsubara dynamics. And this is basically a theory explaining how you can combine sort of the classical-like motions that you get in liquids with the quantum statistics. And this was actually discovered by two former PhD students called Tim Heel and Michael Willett. And what you do with this theory is you feed in the quantum effects from the statistics into the dynamics. So a recent student called George Trenins scaled this up and got what are to date the most accurate simulations so far of liquid water. So a lot of what we're working on at the moment is based on liquid water, and it's being able to basically, we want to be able to simulate everything in liquid water from first principles, including all the quantum effects. So there's quite a lot of projects on that. Another area that's looking very promising is reactions on surfaces. Because you have basically a kind of a friction on a surface from the coupling to the electronic states, it turns out this is exactly describable by this mixture of quantum statistics and classical dynamics. And then finally, another sort of area we're very interested in is, because this is all new physics that came into us, we've been looking at sort of problems that the physicists hadn't considered, and we've come up with new physics in turn. So we're taking some of this back into the theoretical physics sort of arena. So one thing we're looking at is something called quantum chaos, for example, which is a really quite delightfully nasty subject. My group is very democratic, so most of these new ideas were actually discovered by students, not by me, because developing new theory is very much a young person's thing. You need to have a young mind, and so it's a good opportunity, this kind of work, if that's what you're interested in, you want to develop new theory. This is a good field to work in. We're a very small group, 4 or 5 people, and we basically meet up every day to have tea, or at the present time via Zoom, and we discuss a mixture of random topics and usually end up discussing theory. So a lot of the new ideas that we've come up with have come out of these informal discussions. So that's basically the way the group works.